Now, before we get started, are there questions on the homework? Question. Okay. Questions on any of the assignments? All right. So, the table shows several polynomial equations and their solutions, included repeated solutions. Notice that for the last equation, the repeated solution x equals -1 is counted twice. So we have three equations here. The first one, they didn't write it, but we have x to the first. So the degree is 1, and if we solved it, the solution would be 1/2. Number of solutions is 1. Our second equation, x squared minus 2. The degree is 2, and if we went about solving it, the solutions are plus or minus the square root of 2. We have 2 solutions. Our third one is a cubic. The degree is 3. Our solutions, if we solved it, are 2 and -1 plus or minus I squared root of 3. So we have a total of 3 solutions. And our last one, x cubed plus x squared minus x minus 1. The degree is 3. The solutions are -1, -1, and 1, giving us a total of 3 solutions. And it kind of leads into the fundamental theorem of algebra. If a polynomial of degree n, where n is greater than 0, we actually have a equation, then the equation f of x equals 0 has at least one solution in the set of complex numbers. And that's easy to achieve, because if we said the solutions for a given polynomial are x is equal to 2 and x is equal to 1, well, I can say one of them is x1 plus 0i. It's now a complex number in the complex plane. So, or any number is in the complex plane, it just might not have an imaginary part to it. Now, the more important piece is the corollary of the fundamental theorem of algebra. If we have a polynomial of degree n where n is greater than 0, then f of x equals 0. Our solutions, we have n solutions. So the degree and the number of solutions are going to be the same, provided that we count any repeated solution the number of times it's repeated. So if a solution is repeated twice, we count it twice. If it's repeated 3 times, we count it 3 times. So every time it's repeated, we count it that many times. Thus, how many solutions does the equation x cubed plus 3x squared plus 16x plus 48 have? What's the degree? So the degree is 3, so the number of solutions is 3. So that's 3 solutions. We're taking the Chapter 4 test next week, yes. We'll figure that out when we get there. How many zeros does this function have? 4 zeros, 4 solutions. And it works out for this here, the solutions are -2, -2, -2, and 0. We count the -2 3 times and 0 once, giving us a total of 4. How many solutions does x to the 4th minus 2x cubed plus 5x plus 12 have? 4 solutions. Well, at least for these. How many zeros does this one have? 3. Because it's equal to the degree. Okay. Now looking at this one, how many solutions should we have? 5. Okay. So we should have 5 solutions. We do have 5 solutions. We need to find them. And there's different ways that we have to finding in all the zeros. Now looking at this here, we're going to have 5 solutions in the end. And the first thing we're going to do is graph. And when we graph, we want to find at least 3. Because if we can find 3 solutions, we can take it from a 5th degree polynomial function down to a quadratic. And we have ways to solve a quadratic function. So the first thing we want to do is graph this function here and see what zeros we can find. We could also use the rational root theorem, or plus or minus p over q, but either one of these will work. So if we grab the graphing calculator, we'll hit y equals x to the fifth plus x to the third minus 2x squared minus 12x minus 8, and we type it in, we'll hit graph. And we do see that it intersects, it touches the x-axis at one point, looks like -1, and crosses at 2. So if we go second graph, second table, we do see at -1, the y value is 0. -1 is a solution because its value of y is 0. At 2, the y value is 0. So for our solutions, we know x is equal to 2, and x is equal to -1. And at this point here, we will start our synthetic division. So we're going to start with the two solutions that we have, and then we will go from there. So we set up synthetic division, we bring the first number down. Now we do our multiplication. 2 times 1 is 2. 0 plus 2 is 2. 2 times 2 is 4. 1 plus 4 is 5. 2 times 5 is -2 plus 10 is 2 times 8 is -12 plus 16, 4. 2 times 4 is -8 plus 8 is 0. So 2 worked. Well, we knew it was going to work because the graphing calculator told us that the remainder was 0. Now we're going to do the same thing with -1. -1 times 1 is -1. 2 plus -1 is 1. -1 times 1 is -1. 5 plus -1 is 4. -1 times 4 is -4. 8 plus -4 is 4. And -1 times 4 is, and 4 plus -4 is 0. Well, I'll start just writing those down. We have 2 solutions so far. We need 1 more. Now, one thing that is interesting with graphs of polynomial functions, if they touch the x-axis but do not cross, they have an even number of zeros. If they do cross, they should have an odd number. So there's a good chance 1 or 2, -1 or 2 is repeated. I'm going to try -1 first and see if it is a repeated solution. And we can do this again. -1 times 1 is -1. 1 plus -1 is 0. -1 times 0 is 0. 4 plus 0 is 4. -1 times 4 is -4. And 0 plus -4 is 0. So it did work out that -1 was repeated twice. Now at this point here, we could try 2 and see if it is repeated. We bring down the 1. 2 times 1 is 2. 0 plus 2 is 2. 2 times 2 is 4. And 4 plus 4 is 8. Since we have a remainder of 8, 2 does not work. -2 will not work either because it didn't cross at -2. Our other option is that -1 works again. 1 times 1 is -1. 0 plus -1 is -1. 1 times -1 is 1. 4 plus 1 is 5. Thus, neither one of these work again. and there were other ones that showed up. So what we can do is at this point, is put our variables back in. The 0 inside the box is the remainder. Our 4 is our term without x. 0 is our term with x. And 1 is our term with x squared. Telling us that the equation we have left to solve is x squared plus 4 equals 0. Now we could try graphing this. So I can clear this out and say x squared plus 4 graph. Well, I didn't even cross the x-axis. So we have to solve it by other means. Now since there's no middle term, no term with just x to the first, what we can do is get the x squared term by itself. We'll subtract 4 from both sides. Telling us x squared is equal to negative 4. At this point, we'll take the square root of both sides. Our square root and square would cancel, giving us x by itself. And whenever we take the square root of both sides, we add the plus or minus. This also follows with our fundamental theorem of algebra. Because it's a second degree polynomial function, we should have 2 solutions. That's also the reason we add the plus or minus. Now the negative is going to come out as I. Square root of 4 is 2. So our square root of negative 4 is 2i. We have plus or minus 2i. So our solutions for this here are 2, negative 1, and positive negative 2i, which gives us 1, 2, 3, 4, 5 solutions. Questions on this here? Get ready for the next one. Now, if we look at the next one here, the degree is what? 3. So the number of solutions we should have is 3. Now we could start off with the rational zeros theorem, our plus or minus p over q, but I think we'd rather start off by graphing it. Now when we graph this, the number of solutions we want to try to find, rational solutions, is at least 1. Because if we find 1, we can get it to a quadratic and we can solve it from there. Even better if we can find 2. And the best case scenario is that we find all 3. Because if we find 3 zeros, then we're done because we have them all. X cubed plus 7x squared plus 16x plus 12. If we look at the graph here, we have negative 3 and negative 2. We have 2 solutions. Well, we're missing 1. So that's better than just having 1, but not as good as having all 3. And there's a good chance one of these solutions is repeated. Now we can do synthetic division. Negative 3 times 1 is negative 3. 7 plus negative 3 is 4. Negative 3 times 4 is negative 12. 16 plus negative 12 is 4. Negative 3 times 4, negative 12, and 12 plus negative 12 is 0, which is exactly what we wanted to have happen. We can do this again, this time with negative 2. Negative 2 times 1 is negative 2. 4 plus negative 2 is negative 2 times 2, and negative 4 plus 4 is 0. At this point here, we can plug the variables back in. Our number in the box is the remainder. It's 0, just like we wanted. The 2 is our term without x. 1 is our term with x. Telling us what we have left, our last polynomial, is x plus 2 is equal to 0. At this point here, we can subtract 2 from both sides. telling us our last solution is x is equal to -2. Which means on the graph, where it intersected at -2, it just touched the x-axis and went back up. It never actually crossed there. Questions on this here? We ready for the next one? X to the fifth minus 3x to the fourth plus 5x cubed minus x squared minus 6x plus 4. Again, let's type it into the graphing calculator first. Let's let it do some of the heavy lifting. We have this here. And if we look at the table, we do have that -1 and 1 are zeros. And if we look at the graph, it does cross the x-axis at -1, and it looks like it touches the x-axis and goes back up at 1. So there's a good chance 1 might work more than once. -1 might work exactly once. Now the number of solutions when we're done should be 5 because it's a degree 5. We need 3. So let's use -1 and 1 first, and then we can go from there. Yep. -1 times 1 is -1. -4 plus -1 is -5. -1 times -5 is 5 plus 5 is -1 times 10 is -10. -1 plus -10 is -11. -1 times -11 is, okay. There's an error there. Does anybody see it? Because, I mean, if we kept going, we would get 5, -5, not 0. But there is an error on that top row. Yeah, because this is not 4, it's supposed to be what? 3. Yep. Well, before I do that, because that's fine, but the rest of this. Is not going to work, because that's supposed to be -3. And I mean, that's good that that happened. Well, it's not good that it happened, but it's good also. Because it also is telling us, the graphing calculator told us -1 worked. I realized at a certain point I'm not going to get 0. So then I look back and see what might be wrong with that top row. Should be -3, not -4. Now when we add it, -3 plus -1 is -4. -1 times -4 is 4. 5 plus 4 is 9. -1 times 9 is -9. -1 plus -9 is -10. -1 times -10 is 10. -6 plus 10 is 4. -1 times 4 is -4. And lastly, our 4 plus -4 is 0. So that worked the way we wanted. Now the other one we have is 1. Our 1 times 1 is 1. -4 plus 1 is -3. 1 times -3 is 9 plus -3 is 1 times 6 is 6. -10 plus 6 is 1 times -4 is, gives us 0. Now it is possible to solve it from here, but we saw that one of these zeros is probably going to repeat, and that one is 1 because it came down, touched the x-axis, and went back up. So we can do this one more time. 1 times 1 is 1. Negative 3 plus 1 is negative 2. 1 times negative 2 is negative 2. 6 plus negative 2 is 4. 1 times 4 is 4. And negative 4 plus 4 is 0. So in this case here, 1 worked twice. Unfortunately, 1 will not work again, and negative 1 will not work again. So we're going to put our variables back in. The number in the box is our remainder, and it is 0. The number in front of it, 4, is our constant term, our term without x. Our negative 2 is our term with x, and 1 is our term with x squared. Now, unfortunately for this one here, we can't use the square root method because we do have a middle term. We do have an x term. So we're going to use the quadratic formula. A is the number in front of x squared, which in this case is 1. B is the number in front of x, and C is our constant term, our term without a variable. And this is all referencing back to the general form of ax squared plus bx plus c. So at this point here, we can plug it into the formula. Negative b, so it'd be negative, negative 2, plus or minus the square root of b squared, negative 2 squared, minus 4 times a times our c value, which is 4, all over 2 times a. At this point here, we can do some simplifying. Our negative, negative 2 is just going to become 2. The denominator, 2 times 1 is 2. We can plug everything inside the radical into the calculator. Negative 2 squared minus 4 times 1 times 4 is negative 12. Unfortunately, we can't plug the square root of negative 12 into the 30xs as it is. But what we can do is think of the square root of negative 12. Well, the negative is going to come out as I, leaving us with the square root of 12. Now we can plug the square root of 12 in, and the square root of 12 is 2 square root of 3. So square root of negative 12 is 2i square root of 3. Now at this point here, both terms, when I say both terms, I mean these two terms here are both divisible by the denominator, which is 2. And our 2 divided by 2 would give us 1. And here our 2i divided by 2 would just give us I with our square root of 3. And that there is our last two solutions. So all of our solutions were negative 1, 1, and 1 plus or minus I square root of 3. Questions on this here? The last theorem that we have is this one here, the complex conjugate theorem. Complex conjugate theorem states if a plus bi is an imaginary zero, a solution, then a minus bi is 2. So if we get 2 plus I as a solution, its complex conjugate 2 minus I has to be a solution as well. If we have one, we have to have the other. So, just like we did yesterday with finding the polynomial function given the zeros, we're going to do the same thing here. Now this here tells us that one of the solutions, one of the zeros is 2. It tells us the other one is 3 plus I. Since 3 plus I is a solution, 3 minus I also has to be a solution. If we have one, we have to have the other. And just like yesterday, the first thing we need to do here is get each one of these three equations equal to 0. So for our x equals 2, we will subtract 2 from both sides and get x minus 2. For our x is equal to 3 plus I, first thing we can do is subtract 3 from both sides, telling us x minus 3 is equal to I. At this point here, we can subtract I, telling us x minus 3 minus I is equal to 0. And then lastly, the last one, we'll do the same thing. We'll get it equal to 0, so the first thing we'll do is subtract 3. Telling us for this one here, x minus 3 is equal to negative I. So instead of subtracting I for this one here, we will add I, telling us x minus 3 plus I is equal to 0. Questions on this here before we move on to multiplying? Now, just like yesterday, to get the polynomial function, we're going to multiply these all back together. And just like with our radicals, I would multiply our complex conjugates, our terms, our parentheses with I together first before we multiply it with the other one. So our x minus 3 will just come down. And in our second set of parentheses, we're going to distribute the x first. X times x would be x squared. X times negative 3 would be negative 3x. And x times I would be plus xi. Our next step would be distributing the negative 3. Negative 3 times x, negative 3x. Negative 3 times negative 3 would be plus 9. And lastly, negative 3 times I is negative 3i. Then our last multiplication is going to be with, not x, is going to be with our negative I. Negative I times x is negative xi. Negative I times negative 3 is plus 3i. And negative I times I is negative I squared. Now at this point here, we do need to do some simplifying. We'll still have our x minus 3. Then our second set of terms, positive xi, negative xi, those become 0. Negative 3i plus 3i, that is 0. Our other like terms, x squared doesn't have any other like terms, so it stays x squared. Negative 3x minus 3x is negative 6x. Plus 9 minus I squared, by definition, is negative 1. So we have minus negative 1. Well, 9 minus negative 1 is the same as 9 plus 1, which would make this plus 10. Questions on how we got to this point here? All right. We're going to finish this up by multiplying again. X times x squared is x cubed. X times negative 6x is negative 6x squared. And x times 10 is plus 10x. We'll distribute the negative 3. Negative 3 times x squared is negative 3x squared. Negative 3 times negative 6x is plus 18x. And negative 3 times 10 is negative 30. And very last step, we combine like terms. X cubed doesn't have any like terms. Negative 6x squared minus 3x squared is negative 9x squared. 10x plus 18x is plus 28x. And then we have our minus 30. And that's it there. Questions on this one here? Okay. We'll stop with this one here, and we're going to finish this note sheet tomorrow.